Hello, and welcome to the third in a series of 4 lectures on electric power quality. My name is Ben Stevens. I am a research assistant to Professor Surya Santoso at the University of Texas at Austin. This lecture will cover the characteristics and causes of voltage sags and momentary interruptions, as well as the effects of these phenomena and practices used to mitigate them. As discussed in the second lecture, IEEE Standard 1159-2009 classifies power quality disturbances according to duration, magnitude, and spectral content. Voltage sags and interruptions, which we will discuss in this lecture, are classified as RMS variations, so called because their duration is long enough to have a noticeable effect on the root mean square voltage or current values of the power system. This is in contrast to transients, phenomena that are too brief to be identified through changes in RMS values. RMS variations are grouped into 2 main categories according to their duration. Short duration variations last for less than 1 minute, while long duration variations persist for longer than 1 minute. A voltage sag occurs when the RMS voltage magnitude falls between 10% and 90% of its nominal value. In the figure, a disturbance occurs at about 0.02 seconds, causing the voltage to sag to 30% of its nominal value of 7.2 kV. Put another way, this is a 70% sag. The sag persists for about 5 cycles before the voltage returns to its nominal value. A voltage interruption occurs when the RMS voltage magnitude falls below 10% of its nominal value. The figure shows a voltage interruption of considerable length, showing both the RMS and instantaneous voltage values. The RMS voltage magnitude falls to 0.096 per unit, just below 10%, constituting an interruption, and it persists for more than 11 seconds before returning to nominal. A voltage swell occurs when the RMS voltage magnitude increases to above 110% of its nominal value. The 2 figures compare the RMS and instantaneous voltages of phases A and B on a power system during a short-circuit fault event on phase A. Note from the timestamps that the 2 figures show the effects on 2 phases of the same fault event. Phase A experiences a voltage sag, dropping to 0.15 per unit for about 0.15 seconds. While it does not experience the fault directly, Phase B experiences a voltage swell, increasing to 1.16 per unit while the fault is on the system. This phenomenon can occur in a system when the zero sequence impedance from the perspective of the fault point is higher than the positive sequence impedance. Because the duration of this disturbance was less than 30 cycles, the sag and swell are classified as instantaneous. The figures here depict a similar event to that shown on the previous slide. Again, note that we can see from the timestamps that both figures show the effects on 2 different phases of the same event. In this case, however, the fault, this time on phase C, is much longer lived, lasting for about 1.3 seconds before the voltage sag is corrected. As both the sag and the swell have durations longer than half a second, they are classified as momentary. These figures represent 2 separate events, the left figure showing a voltage sag lasting 5.8 seconds, the right figure showing a voltage swell occurring about 2 minutes later and lasting for 3.7 seconds. Due to their durations lasting longer than 3 seconds, these disturbances are both classified as temporary. These figures show 2 separate voltage interruptions of differing durations. On the left, the voltage falls to 0.096 per unit, lasting for about 11 seconds. As this duration is between 3 and 60 seconds, this is a temporary interruption. On the right, the voltage falls to 0.083 per unit, lasting for almost 2 minutes before returning to nominal. As this disturbance lasted for longer than a minute, it is called a sustained interruption. There are a number of ways to characterize a voltage sag event. Of those listed here, the most important to power quality are the magnitude and the duration of the event. There are 2 ways to describe the magnitude of voltage sag. It can be reported by the RMS magnitude of the voltage during the sag, also called the retained voltage. In this case, the voltage sags down to 0.3 per unit. It can also be reported by the depth of the sag, or the per unit difference between the RMS value during the sag and the nominal value. In this case, the voltage experiences a 70% sag. All reported values are measured at the lowest value of the RMS voltage that occurs during the sag event. The duration of the sag is also important, as both magnitude and duration will determine the response of loads and protective equipment. The duration of a voltage sag is defined as the length of time from the moment when the RMS magnitude of the voltage falls below 0.9 per unit to the moment when it returns to above 0.9 per unit. In the figure, the duration is about 0.09 seconds, or about 5 cycles. Ultimately, the most important consideration when it comes to a voltage sag or interruption is the effect it will have on equipment served by the affected system. Equipment sensitivity refers to the way a piece of equipment reacts when exposed to abnormal voltage conditions. Typically, both the magnitude and the duration of a sag determine equipment response. In general, the larger the magnitude of the voltage sag, the shorter the duration that equipment can withstand it. There are two curves that are often used to describe this magnitude-duration relationship: the Computer Business Equipment Manufacturers Association, or CBEMA curve, and the Information Technology Industry Council, or ITI curve. The CBEMA curve is no longer typically used, having been superseded by the ITI curve. This is a visualization of the ITI curve. The y-axis shows the per unit magnitude of the voltage phenomenon, and the x-axis gives the duration of the event. Note that the x-axis is a logarithmic scale. The shaded area, labeled voltage tolerance envelope, designates the region in which the equipment will be able to survive or ride through the disturbance. If the event's magnitude and duration fall outside the shaded region, the equipment will be disrupted. Notice that voltages between 1.1 and 0.9 per unit will not disrupt equipment no matter how long the condition persists. Note also that this curve applies to equipment with a nominal voltage of 120 volts, and equipment with different nominal voltages may have different curves. Shown here is a typical distribution circuit along with some common devices deployed by utilities to prevent and mitigate overcurrents, the most frequent causes of voltage sags and interruptions. Circuit breakers are switching devices that are capable of interrupting current when its magnitude grows too large. Reclosers are a type of circuit breaker with a programmed sequence of opening and reclosing that occurs when fault current is detected. Fuses are circuit connectors with an element that is designed to melt or otherwise be broken by the heat of a large current passing through it. When a short circuit fault occurs on the system, customers will experience voltage sags or interruptions depending on their location in the system with respect to the fault. High magnitude current will flow to the fault location, activating protective devices in an attempt to isolate the fault. While fuses can easily isolate a fault, they must be manually replaced after they have blown out, and many faults are only temporary. If the fuse blows, downstream customers will experience a sustained interruption while workers replace the fuse. Therefore, reclosers are often coordinated with the fuses to clear temporary faults, with downstream customers experiencing momentary interruptions, giving the fault time to clear and saving the fuse from blowing. While recloser operation often causes momentary interruptions for a larger number of customers, they may help prevent sustained interruptions caused by blown fuses. Voltage sags are mainly caused by short-circuit faults, as mentioned in the previous slide, or by the starting of large motors. In both cases, the root cause is a large current being directed to a particular location in the distribution system. Interruptions are typically caused by the operation of protective devices, such as reclosers opening or fuses blowing. Normal recloser operations will result in instantaneous or momentary interruptions if the fault is temporary, while blown fuses and reclosers entering lockout mode for permanent faults will result in sustained interruptions. Fuses are the most common protective devices used in distribution systems. They are inexpensive and do not require any maintenance. As mentioned, fuses operate simply by melting in the event of high current passing through them, cutting off the circuit they protect from the rest of the system. Fuses are intended to blow if the downstream fault is permanent and must be isolated until it can be manually cleared. Fuses come in two types: expulsion fuses and current-limiting fuses, which differ in the manner in which they extinguish the initial high current that melts the fuse element. The response of a fuse to a fault current is determined by the magnitude of the current. Fuses have an inverse time current characteristic, meaning that higher current magnitudes cause fuses to melt in a shorter period of time. This characteristic is defined by two curves, designating the minimum and maximum times that the fuse can take to melt and clear the current at a given current magnitude. Typically, fuses are modeled as melting at the average of the minimum and maximum melting times. This figure shows a typical single-phase recloser. It would be mounted on a pole top and it is insulated with oil. This is another oil-insulated recloser, but this one operates on all three phases. Depending on the model, the recloser may open and reclose all three phases together, or may be capable of operating on one phase at a time. This type of recloser would probably be found in a substation. Here is another type of three-phase recloser. Newer reclosers are not insulated with oil, but rather with a solid dielectric material. Like fuses, reclosers also have inverse time current characteristics. Each recloser has two such characteristics, the fast and delayed curves. For a given current magnitude, the fast curve has a shorter time value than the delayed curve. Reclosers are programmed to open according to one of these curves when it observes a fault current. Fast tripping is designed to be faster than fuse melting times, attempting to allow faults to clear and save fuses from blowing. Delayed tripping is designed to be slower than fuse melting times, giving fuses time to blow and isolate permanent faults. Reclosers are programmed to follow a sequence of fast and delayed operations. The two most common sequences are one fast operation followed by three delayed operations, or two fast operations followed by two delayed operations. The recloser will remain open for a reclose interval between each operation. These reclose intervals are typically 1 to 2 seconds long, although the first interval may be as short as 12 to 30 cycles. As mentioned, recloser operations are coordinated with fuse melting times, such that the fuse melting time curves fall between the fast and delayed curves of a recloser. This ensures that a recloser fast operation occurs before the fuse can blow, thereby saving fuse elements in the event of a temporary fault that clear during the reclose interval. If the fault is permanent, the recloser will eventually switch to delayed operations, which take longer than the maximum fuse melting time, ensuring that the fuse will blow and isolate the fault. This type of coordination is referred to as fuse saving. As the majority of faults are temporary, fuse saving operation can prevent many blown fuses, which must be replaced manually and result in sustained interruptions to downstream customers. Instead, downstream customers from the recloser will experience only momentary interruptions during temporary faults. In order for fuse saving to be implemented, there must be a recloser present upstream from the fuse, and the recloser time current characteristics must be coordinated with the fuse melting times, as discussed in the previous slide. For example, in the bottom figure we see a fault occurring on a lateral line protected by a fuse. Upstream from the fuse on the main feeder is a recloser. The time current characteristics of the fuse and the recloser are shown in the right-hand figure. When the fault occurs, both the recloser and fuse will experience a fault current of 3 kA. The recloser, being set to fast operation, will open in 2 cycles before the fuse can melt. The recloser will remain open for its first reclose interval, giving the fault a chance to clear. After the reclose interval, the recloser will reclose. If the fault has cleared, normal operation resumes. If it is still present, the recloser, depending on its programming, will either attempt a second fast operation or else switch to delayed tripping, in which case the fuse will melt after about 9 cycles. Fuse saving is generally advantageous for utilities, reducing the number of sustained interruptions and preventing maintenance teams from having to be dispatched to replace fuses. However, the practice does have some downsides. Recloser operations will cause interruptions to downstream customers and sags for upstream customers that would not have otherwise occurred had the fuse been allowed to blow. Depending on the situation and the customers present downstream, it may be advantageous for the utility to not employ fuse saving.